Hello, good day, students. So I'll be discussing the image enhancement special filtering's second lecture today. So we have already discussed the smoothing part. So here we will be discussing the sharpening part. So before going to the sharpening, I hope you have gone through how we have been done the special filtering. So in this case, what we have here is we'll be discussing the special filtering, whatever we have done in the last class. We'll be just going through a refresher of that. Then I'll be discussing the first derivative and second derivative of sharpening filters, and then we'll be combining the different filtering techniques. So first, what we did in the special filtering, if you remember, is we were convolving two set of matrices. Whatever is the mask of the filter mask, R, S, T, U, V, W, X, Y, Z, was being convolved with A, B, C, D, E, F, G, H, I, where E is the center pixel, and the new processed E is actually combination of this convolution of this mask with the set of pixel. And as this is 3 cross 3 base neighborhood, we'll move the filter over this and we'll go ahead, and the same can be done if it is 5 cross 5, 7 cross 7, and so on, and we'll be getting a modified like E processed will be getting a modified, or say from fxy will be getting f dash xy, which is with the filtered version of fxy. So in sharpening filter, the main thing that we didn't do in smoothing was that we in during smoothing we were removing the finer details. In sharpening, what we do is that we seek to highlight the finer details. So as we need to remove the blurring of the images and highlight the edges, so we'll do spatial differentiation here. Once we go to the frequency domain, I'll be discussing the frequency domain based differentiation. So for example, if we take a real-time case and say this is the image, and there I want to take for one particular line, say if I take from A to B, from in the x-axis you have this set of pixel values 5, 5, 4, 3, 2, 1. So you may have a ramp, isolated point, thin line, flex, segment, step, and other things. And when we do the first order derivative, what we're doing is that rate of change of f with respect to x, as we're doing it in one dimension. So this is fx plus 1 minus fx, which is fx plus 1 is the future value and fx is the present value. We can do it in other way around also, which is there in many books, is fx minus fx minus 1, means present value minus the previous value. So whether you do present value minus the previous value or do future value minus the present value is the same thing, means we are just subtracting the two consecutive terms. So we take the subsequent values and find out the difference, and based on that we find out the rate of change. Rate of change with respect to dx, the denominator part is 1, because when we do x plus 1 minus x is 1, or you do fx minus x minus 1 is again 1. So either you use fx plus 1 and fx, or you use fx and fx minus 1 is the same thing. So this is how we have the first derivative. So 5 minus 5, we have 0, 5 and 4, you have minus 1, minus 1, minus 1. So here it is reducing. So all is minus 1. Then after some time it is constant. So it is constant for 3 values, but here it is constant for 2. Then it increases to 6, so plus 6 increase, then from 6 again 0, so it is a minus 6 decrease, like this, plus 6 minus 6, you can see here. Then again for 4 zeros I have 3 zeros, so it is constant for 3 cases when we have set of 4 continuous values, and so on. The same thing when we do for second derivative is we take the future value, we take the past value and subtract the present value, 2 times of the present value from them. So that is what rate of change of f with respect to x, but it is double differentiation. So you can see here when we do this, here it is minus 1, 0, 0. So edges are being highlighted, so on. If you want to see the program for this, I have done it in MATLAB. You can see this is the same term, defects and defects 1 is there. So defects and defects 1 is double differential. Diff actually does the single differential. So if I do diff 2 times, I get double differential here. You can see how it is happening. So you see whatever I put up in the slide, this is what you are getting. Okay. So this we can do in this way. Now, going ahead, when we do the second derivative for image enhancement, uh, we have stronger response to the finer detail. We have simpler implementation, and the main reason for this is the first smoothing filters that we'll be looking is the Laplacian, which is isotropic, and one of the simplest sharpening filters, and we'll go for the digital implementation of this. So the Laplacian is this particular thing where we are doing double differential with respect to f and x is x, and double differential of f with respect to y, because we go on changing the image in both time and frequency in both x and y axis. So as it is in both x and y axis, so we have to individually do double differential of f with respect to x and double differential of f with respect to y. So when we take into this, we have the future value, past value minus the present, two times the present value for the x-axis, and the same thing for the y-axis. So when we put them together, these are nothing but the horizontal and the vertical axes near, or those neighborhood points which are having a distance of 1. So the combination of del square f is nothing but this two terms together. So this is represented as this particular mask, where these are the neighborhood 4 pixels, the nearest neighborhood 4 pixels, and the center pixel. Now, when we apply this, what happens? This moon image is generating this filtered image. So if we scale it for viewing, it is like gray, but actually it is the edge or binary image kind of thing that is coming. So what we do here is that the edges are highlighted. Now to highlight the edges more, we subtract this Laplacian image from the original image. So original image minus Laplacian is the enhanced or sharpened image, because those finer details have been sharpened. So when you do this, this operation uh, is like this. So if we're doing two original image minus the Laplacian, so we can directly put them there, and we have a modified version here. So the initial matrix, which was in this format, has now, from this 1, 1, 1, and 1, and center being -4, has changed to uh, a new version. So the new version that we have here is here. So combination is giving me this. So we have a new simplified image enhancement based on this, where this +1 has become -1, and -4 has become +5. So if we include the diagonal pixels, these four diagonals, then that term from -4 becomes -8, and the total thing from will become -1 series, and the center being 9. So we can do any of them and see the result. So based on that, we can have the different first derivative filtering with respect to the Laplacian, and we can have various masks coming out. So if you want to see that, this is the first matrix where we are having 0, 1, 0, 1, -4, 1, 0, 1, 0. So when I use this mask here, then we have one image as this one, and then we do this k equal to I minus j after calculating j. The same thing is done here using for sharpening 2. I have the same thing, only difference is that instead of 0, 1, 0, it is 1, 1, 1. Then instead of 1 minus 4, 1, I have 1 minus 8, 1. And instead of again 0, 1, 0, I have triple 1. So when I put this, this is the diagonal thing containing this, so the same another j will come up. So when you subtract this k I minus j or that k I minus j, I get a modified version. So going ahead, if you go for the sharpening thing, here you are having h 0, and as we go ahead, we are having these two together. So you can see the difference. This is the first sharpening, the second sharpening. If you compare the two, you see the second sharpening and first sharpening. The first one is more sharpened, and if you directly apply them, this is the condition, original derivatives. So it's the same thing, just applying these matrices one by one. Next, we go for the Sobel operators where we have -1, -2, -1. This is the horizontal, and with respect to corresponding, I have 1 to 1. And similarly, -1, -2, -1, and 1 to 1. This is for horizontal and vertical. So by this, we can enhance the horizontal and vertical components. You can have a look in this one. So I have this, the horizontal, and this is for the vertical. You can see here in one, the horizontal things are highlighted, and here the vertical things are lines are there. And based on that, we are having a sharpened horizontal image and sharpened vertical image. So Sobel filters are for edge. So we have first order derivative generally producing thicker edges, second order derivatives which have stronger response to finer details or thin lines, and the first order derivatives have stronger response to gray level step, whereas the second order derivative produce double response at the step of every change in the gray level. So to summarize, we have sharpening filters using first derivative and second derivative. So going if we look into this, we can see the combining of the filtering techniques. So if you see here, this is a successful image where we are having this skeleton image which we want to do step-by-step modification. So in this image, what we are doing first, we are sharpening this, applying Laplacian filter of the bone scan. So this is the bone scans coming. Then we sharpen it and we get a bit brighter cane. Then by applying Sobel filter, we get the vertical and horizontal edges, and then you smooth you with uh, 5x5 averaging filter, and then filter it, and the sharpened image is the sum with this. After that, if we do power law transformation, the bones are more easily visible. So this is just an operation, and you can do millions of this kind of operations time to time. So you can have a look in this kind of operations for image enhancement and producing great pictures. So thank you for now. Thank you all. So if you have any doubts, you can contact me in the class.